Hello students, today we are going to understand a very important concept in physics, resonance in an AC circuit. In an AC circuit, we have three components, a resistor, an inductor, and a capacitor. An AC circuit may also contain any two of these three components connected in series as shown. Each of these circuit components affects how current flows in the circuit. In our previous lessons, we have learned that the inductor gives inductive reactance and the capacitor gives capacitive reactance. These depend on frequency, meaning when frequency changes, their values also changes. If we look at the circuit with only an inductor and a capacitor, when inductive reactance is bigger, the circuit behaves like an inductor. Voltage leads current by 90 degrees. When capacitive reactance is bigger, it behaves like a capacitor. Current leads voltage by 90 degrees. In practice, this case does not truly exist because every inductor has some resistance, even if it's very small. Now, here's the interesting part. At a particular frequency, something special happens. The inductive reactance XL becomes exactly equal to the capacitive reactance XC in magnitude but opposite in phase. So they can cancel out each other. XL is equal to XC. And this condition is called resonance. XL is equal to XC. Omega L is equal to 1 over omega C. Since omega is equal to 2 pi f, substitute. 2 pi fL is equal to 1 over 2 pi fc. Rearranging, 4 pi square f naught square LC is equal to 1. F naught square will now be equal to 1 over 4 pi square LC. F naught will be equal to square root of 1 over 4 pi square LC. F naught is equal to 1 over 2 pi LC square root. At resonance, the circuit behaves like it has only resistance. The impedance becomes minimum, where Z is equal to R, and the current becomes maximum. This is the point where the circuit works most efficiently. The frequency at which this happens is called the resonance frequency. A graph of inductive reactance against frequency gives a straight line, while a graph of capacitive reactance against frequency gives a curve. The point where the two graphs intersect is the resonance frequency. Resonance is used in real life for selecting specific signals in radios, televisions, and communication systems. Sharpness of resonance depends on resistance, R. Low resistance, sharp resonance. High resistance, broad resonance. Example. The power factor of a series RLC circuit at resonance is... At resonance in a series RLC circuit, inductive reactance is equal to capacitive reactance, so they cancel out. This means the circuit becomes purely resistive. Voltage and current are in phase. The power factor is cos phi. At resonance, phase angle phi is equal to 0. So cos 0 is equal to 1. Final answer B, 1. If this video have helped you gain clarity, don't forget to subscribe and share with your classmates. In our next video, we'll be treating more problems on resonance in an AC circuit. Thank you for watching.